Hello everyone. I hope I'm audible and my screen is also visible. The whiteboard is also I hope visible. Please, if possible, please someone confirm it whether I'm audible or not, clearly at least, and screen is visible or not. Or if is there any issue, please let me know. Good evening. So I hope I'm audible, right? Yeah. Thank you for confirming. So as like to the previous tutorial, so in today's also, if you have any issue with the assignment problems or any problem to the content of this course, you can ask me here. I'll try to explain that. I'll try to solve those problems, and 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 also I'll try to do some problems which may help you to solve the next assignments. And in the during this tutorial, if you face any problem regarding the uh, my voice or the screen visibility or anything regarding the technical issue, you can ask me. If I'm not able to hear you, you can write in the comment section so that I may read that and try to fix this issue. And if you have anything which I'm going to explain or I'm going to discuss, if those things are not able to understand, you can ask me. Even if I have solved that problem in the previous tutorial or in this tutorial or anything which is which is not able to understand to you, not able to clear to you, you are not clear on those things, you can ask me. I'll try to solve or explain those things. So if you have any problem, you can ask. Meanwhile, I am trying to solve a problem. So this is one problem. So what it says, let T be a non-zero nilpotent linear operator on a finite dimensional vector space V over F, then which of the following statement is or are incorrect? So the question is or are incorrect. That means multiple option can be incorrect. And so as like the previous tutorial, here is also I will not explain the theorems in I will not explain any theorems or anything unless it is required. I will explain those things, or any terminology which are required I will explain during that during when I will try to solve those problems. Okay. So here is one new term, that is nilpotent. I will explain this, and you may know this what is the nilpotent means, but still I will explain. So if what are the options? The question says that it be a non-zero nilpotent linear operator on a finite dimensional vector space V. Finite dimension is also given. Then which of the following statement is or are incorrect? First question: if dimension of V is n and n is greater than 1, the characteristic polynomial of T is the minimal polynomial. So what is the characteristic polynomial and what is the minimal polynomial? Those two terms also I need to mention. And second is that T cannot be, okay, let T be a non-zero nilpotent linear operator on a finite dimensional vector space. T is given that T is a non-zero nilpotent linear operator on a finite dimensional vector space. So in that case, T is T. So another option is T can't be diagonalizable. Another option is that um, if index of T is R and the dimension of V is n, then the degree of the minimal polynomial is R. Okay. If index of T on V is R and dimension of V is n such that R is greater than equals to 3, then T may be diagonalizable. Okay. So we'll see, but there is many terms. What are the terminology here? First term is the what is the nilpotent linear operator. Second term is that characteristics polynomial. Third term is that minimal polynomial, and fourth term is already known, that diagonalizability. Okay, so I'll explain those terms one by one. And so what is nilpotent? A linear operator T that can be on a finite dimensional vector space or on an infinite dimensional vector space, that doesn't affect. A linear operator T on a vector space V, on a vector space V, is said to be nilpotent if there exist if there exists a positive integer that can be 0 also, not 0, sorry, that can be 1 also, positive integer a r such that t to the power r is actually the 0 operator. That is, t to the power r is a 0 operator. That is, t to the power r is the 0 operator. 0 operator is that operator which sends every element to 0. Okay, that is a linear operator. So that means a linear operator T is said to be on a vector space V is said to be nilpotent if there exists a positive integer r such that t to the power r is equals to 0. That means if we do something repeatedly, so I may get, for example, if I consider t from r2 to r2, how I am giving that t is mapping a1 a2 to 0 a1. So now if t square is mapping, then where t square will map? T square will map that t of 0 a1. So that means it is shifting the term to the right hand side position. So a1 is shifted to a2 place and a2 is shifted to 0. So then this will be like 0 comma 0. So that means t2 is a nilpotent linear operator. So this is nilpotent linear operator, and this is a non-zero linear operator, right? Because t is sending some non-zero entries to the non-zero entries. That's not sending every non-zero entry to the zero entry. Okay, that's why t is nilpotent. A zero operator is that operator which sends every element of the vector space, wherever it is defining, to the 0 element. Okay, so t is here, it is non-zero operator, that is clear. And another thing is that t is a nilpotent linear operator because the repeated application of t is making it to sending it to 0. Okay, so this is the nilpotent linear operator. So now what is the index of a nilpotent linear operator? Is the smallest positive integer. Index is, for a nilpotent linear operator, index for a nilpotent linear operator is the smallest positive integer, r such that t to the power r is equals to 0, but t to the power r minus 1 is not equals to 0. That means t to the power r minus 1 sending at least a non-zero entry to a non-zero entry. Okay, so this is what it is, the index. That means the smallest power which makes the operator t 0. So for example, here in this example, you can look at t to the power 3 is also 0, but t to the power 2 is also 0. That's so, but t to the power 1 is not 0. So that's why here the index of this nilpotent linear operator is 2, not 3, not 1. Okay, so this is the index. So another what are the terminologies there? Characteristics polynomial and the nilpotent minimal polynomial. So characteristics polynomial, for characteristics polynomial we need to be a linear operator on a finite dimensional vector space. Otherwise characteristics polynomial does not making sense. Characteristics polynomial. For a linear operator T from to V to V over on a finite dimensional vector space, finite dimensional vector space V is said to for a linear operator, this is the characteristics polynomial is determinant of xi minus the matrix representation of t with respect to any order basis b. Okay, this is the polynomial. Okay, so because this is determinant, this will be polynomial, where TB is the matrix representation of T with respect to any order basis beta of V. So what it says, this says that if you have a linear operator T, you have to first do what you have to find the matrix representation of that linear operator T with respect to any order basis, and you have to find the determinant of xi minus tb. So basically what it is saying, characteristics polynomial. So what one more thing one can from here say, that I am saying with respect to any order basis. So if you change the order basis, still the characteristics polynomial will be same, because if you change the order basis, then the matrix representation will be converted with respect to new order basis. That will be something like this for an specific invertible in matrix P. So if you have a order basis beta, another order basis beta dash, so then the matrix representation of T with respect to the different order basis is given by this for some specific matrix P, that's called the basis change matrix. So in that case, you can look at, if you consider the matrix, this is the matrix for this matrix, then you can check this is easily that xi minus tb is equals to determinant of xi minus tb dash. So that means for any order basis, the characteristics polynomial is same. And in fact, the roots of these characteristics polynomials are actually eigenvalue for the linear operator T. Okay, but it is not saying anything about the power of the or the degree of the. I mean, whenever you have if, then we can say, then if C1, C2 all the way Ck are a distinct eigenvalue, or sometimes it is also called characteristics value of T, then characteristics polynomial which is in general denoted by fx, which is actually determinant of xi minus matrix representation of 2 with respect to any order basis B, is equals to x minus c1 whole to the power some d1 all the way x minus ck whole to the power some dk. So all the di's are at least greater than di's are integers called algebraic multiplicity. Di's are integers, positive integers called algebraic multiplicity, of C, called algebraic multiplicity of Ci. So basically di's are the algebraic multiplicity of the characteristics value Ci. Okay, that is the number of repetition of that eigenvalue. This is what it is saying. And obviously you can look at from here, if the matrix if the T is if from here one can look at, if dimension of V, the vector space over which the linear operator T is defining, that is n, then the summation d1 plus d2 plus all the way dk is equals to n. And you can look at clearly that as each di are positive integers, so therefore k can't be more than n. K will be always less than equals to n. So therefore, for a linear operator T on a finite dimensional vector space V of dimension n, the number of eigenvalues will be always less than equals to n. Okay, because there T will be a matrix with respect of order n by n, and determinant of xi minus tb, that will be in itself is a, I mean, that will be a polynomial of degree n, not more than n. Okay, so that means and also note that, fx, the characteristics polynomial, is a monic polynomial of degree n. So what is mean by monic polynomial? Monic polynomial is that a polynomial is said to be monic polynomial if the coefficient of the highest power, that is, suppose you have a polynomial f of x is equals to x to the power a naught x to the power a naught plus a1 x plus all the way plus a k x to the power k, then this x to the power k is the highest degree entries. This is k is called the degree of the polynomial, and the coefficient of the highest degree term, that is actually ak. If that ak is equals to 1, then it is called the monic polynomial. Okay, so the characteristic polynomial is always a monic polynomial of degree n. This is also a fact. You can check because the determinant of xi minus tb, so that will at least turns out to be a polynomial of degree n with the coefficient of x to the power n is actually 1. Okay, so this is the monic polynomial. Okay, some more facts that we need the minimal polynomial. Okay, so what is the minimal polynomial of a linear operator? Okay, so if t is a linear operator, if t from v to v be a linear operator, then uh, for any polynomial, or sorry, a polynomial p is said to be annihilates t if p of t is equals to 0. So what is p of t means? Suppose px is equals to something like a naught plus a1x plus all the way a m x to the power m, then p of t is nothing but a naught identity plus a1 t plus all the way plus a m t to the power n. So this is what it is mean by the pt. So a polynomial is said to be annihilates the linear operator t if pt is equals to 0. Now the set of all polynomials in over the field f will forms an ideal principal ideal, basically forms an ideal in the field field fx. What is means by here fx? Fx is this is the field. So f is the v is the vector space over the field f. That is what it is considering. V is the vector space over the field f. Okay, f is a field, v is a vector space. For example, you can consider f is either real number or complex number. Okay, so if v is a vector space over the field f, then the set of all polynomials whose coefficients are coming from that field f, which annihilates the set of all polynomials over the field. Oh no, sorry, the set of all polynomials over the field f, which annihilates the linear operator t, which annihilates the linear operator t will forms a forms an ideal in fx, and it was known from the field theory that if f is a field, then fx is actually the set of all the space of all polynomials over the ring of polynomials over the field f is a principal ideal domain. So what is mean by principal ideal? What happens whenever you have a principal ideal domain? Every ideal will be generated by a single element. Okay, that is what it is by principal ideal domain, and that fixed single element, in this case will be called the will be called the minimal polynomial, and it will be turns out to be that polynomial is a monic polynomial. Okay, linear operator t forms an ideal in fx, then fx being principal ideal domain, fx being principal ideal domain, here I am giving some name of this ideal, that what is usual notation for the principal ideal domain for which are annihilates the linear operator t is usually considered What are the notations for the principal ideal domain usually considered for? Okay. Okay. So the fx being principal ideal domain, the ideal of annihilators, the ideals of annihilator ideals of annihilator of T is generated by a monic polynomial called called minimal polynomial for T denoted by mx. This is the general minimal polynomial. So what is the minimal polynomial basically? Okay, in very simple language, minimal polynomial, that is a monic polynomial. First, second is that mt mx is a monic polynomial. Second is that mt is equals to 0. And third is that for any polynomial p, if pt is equals to 0, that should imply that p is equals to m into q for some polynomial q of positive degree. Okay. So if p is not m, basically what it is saying, that any polynomial which annihilates the linear operator t, that will be divisible by that monic polynomial. Okay, monic polynomial is the smallest polynomial for which some sense smallest polynomial for which mt is equals to 0. So therefore, if you take a linear operator and these are the facts. Okay, now two more theorem I will just state, I will not use anything. So first fact, that is actually due to Cayley. Okay, this is Cayley Hamilton theorem, I think. Sorry, not Cayley, what is called, Cayley's theorem only, just only Cayley's theorem. Just so then I will just take the terminology what it is. Cayley Hamilton. Okay, so first fact is that um, mx divides fx. That means characteristic polynomial, sorry, minimal polynomial divides the characteristic polynomial. This is called Cayley-Hamilton theorem. Cayley-Hamilton. This is due to Cayley-Hamilton. This is called Cayley-Hamilton. Okay, the Cayley-Hamilton theorem. So also one more fact is there, that the roots of the characteristic polynomial is exactly same with the roots of the minimal polynomial. Okay, so that means if we write the characteristic polynomial in this way over the algebraic this way, here is some problem. No, this is not true. Then if this is not true, this is true when the field F is algebraically closed. For example, complex field. Okay. Okay. So Cayley-Hamilton theorem is this, and the second fact. This is another first fact. Second fact is that a linear operator. This is very important theorem, not only a fact. Linear operator T on a finite dimensional vector space is diagonalizable if and only if the minimal polynomial mx is completely factorized. That is minimal polynomial must be something like x minus c1, x minus c2. It's not only completely factorized, sorry, linear factors, completely factorized in distinct linear factors. So what it is saying that if a linear operator T will be diagonalizable, that means there exists an basis consisting eigenvectors for the linear operator T or for V, such that if and only if, that is diagonalizability, if and only if the minimal polynomial for the linear operator T is completely factorized into distinct linear factors. That means minimal polynomial should not be contained like this, that x minus c1 to the power 2 or some other repeated factor. Okay, this is what it is, the diagonalizability criteria. So I hope this theorem is very clear, because if this is not clear, you can ask, I'll try to explain it once again. But because this is very important theorem, and this is very simple and important theorem and very useful theorem, because this will I mean, always will help you to discard whether a linear operator is diagonalizable or not. So if the linear factors is completely not factorized in distinct factors, then it is. If the minimal polynomial is not completely factorized in distinct factors, then um, it is not diagonalizable. Okay. So for a diagonalizable operator, this is a fact one can say. For a diagonalizable operator T on a finite dimensional vector space V, the characteristics polynomial fx must be of this form: x minus c1 whole to the power some d1, x minus ck whole to the power some dk. Okay, because characteristics polynomial and minimal polynomial must have same roots, and the minimal polynomial, if the minimal polynomial is look like this way, then characteristics polynomial should be also look like this way. There will not be any other roots. Okay, till now whatever I have said, is there any doubt or any repetition you need, or anything it's not clear? Please let me know, because on the basis of this there will be lots of problem which we are going to discuss. Okay. Okay, so if you don't have, or you can, even if you have, you can ask me. I am. I'll go to above slide. Go to this above pages, and I'll try to explain if you have any doubt regarding this. Till now, whatever I have tried to explain or try to point out. So once again, let's start this problem. And so now, whatever the facts I have mentioned, on the basis of those facts, this problem will be very easy. Okay. So 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 let me once again read that T be a non-zero nilpotent linear operator on a finite dimensional vector space V. Then which of the following statement is or are incorrect? Okay. So first of all, T be a non-zero linear operator. Okay, but T is nilpotent linear operator. So let's take the index of T. Let index of T is equals to R. Remember that what is the index of T? R is the smallest positive integer such that T to the power R is equals to 0. That is R is the smallest positive integer such that t to the power r equals to 0. But fact that t is non-zero. That means as t is non-zero, so r should be strictly greater than 1. That's clear. Because if r is 1, then t will be 0 operator. But here it is mentioned that t is a non-zero linear operator. So r must be something bigger than 1. Okay, positive integer bigger than 1. If dimension of, so let's read the first thing, that if dimension of v is n, then the characteristic polynomial of t is the minimal polynomial. That's not true. Okay, for example, so that means this is the correct option. So question is, what is the correct option? This fact is not true, so therefore as an option this is correct. So this is fact is not true, that's why as an option it is correct. So what is the option? It says that if the dimension of v is n, then characteristic polynomial of t is minimal polynomial. So as I have said, the minimal polynomial is the smallest, minimal polynomial is the, polynomial p such that m of t is equals to 0, and m is the monic polynomial and of smallest degree, right? The smallest monic polynomial, and any polynomial which annihilates the linear operator t, that will be divisible by the minimal polynomial m. So now, for example, for option A, let's take the linear operator A is equals to 0, 1, 0, 0, 0, 1, 0, 0, 0. So clearly, you can look at that the characteristics polynomial E of A will represent a linear operator from F3 to F3. That is by T with the linear operator from the field F3 to, or you can let's consider it is from R3 to R3, and how it is giving T of the vector x is a column vector, is equals to Ax. This is the linear operator. Okay, characteristic polynomial for A is 3, because x minus x identity minus A, determinant of x identity minus A means x minus 1 0 0 minus 0 0 x minus 1 0 0 x, and its determinant is actually x cube. Okay, not 3x, is x cube. Okay, but what is the minimal polynomial? Minimal polynomial is actually uh, the polynomial for the smallest degree polynomial. The ideal of the generator of the ideal which annihilates the linear operator t. So, but look at the carefully that t square is equals to 0, 1, 0, 0, 0, 1, 0, 0, 0, and the similar same thing 0, 1, 0, 0, 0, 1, 0, 0, 0. This says this will be first term will be 0, second term will be 0, third term will be 1. Okay, so that means, so let's change it 0 minus 1 0. So this is the, I'm changing the linear operator. So right now 0 1 0 0 1 0. So this will be like 0 first term, 0 third term, 0 last term is also 0, and all will be 0 because all the rows are 0. So that is says that t square is equals to 0, but t is not equals to 0. So that says the minimal polynomial for linear operator t is x square. So therefore, if here it is mentioned, if n is greater than 1, so clearly here the dimension of the R3, so here n is equals to, 3, so that is greater than 1. So in this case, the characteristic polynomial of t is x cube, but the minimal polynomial for t is actually x square. So therefore, that is not equal. T cannot be diagonalizable. That is a true statement, so that means this is a false answer. Here, for a non-zero nilpotent linear operator is not diagonalizable. A non-zero nilpotent linear operator is not diagonalizable. Why it is? Because for a non-zero nilpotent linear operator, because for a non-zero nilpotent linear operator T from a vector space V to V with dimension of V is equals to n. The characteristic polynomial, this is a fact, characteristic polynomial is x to the power n. This is the characteristic polynomial, and minimal polynomial that is mx, that must be x to the power k for some positive integer k less than equals to n and k is strictly greater than 1, because k can't be 1, because if k is 1, then what I will say, that as mx is the minimal polynomial, so mp must be 0. But if k is equals to 1, that says t equals to 0, that will say that t is a zero linear operator, but it is mentioned that t is a non-zero linear operator. Okay, now let's come to the another fact. What we know, that a linear operator T is diagonalizable if the minimal polynomial is completely factorized into distinct linear factors. But if k is greater than 1, so in this case, the only linear factors is x, and that is not distinct. That means the minimal polynomial is not able to factor into distinct linear factors. It has a repetition. Okay, so as it has a repetition, there is one theorem I have said, that's very important theorem, that a linear operator T is diagonalizable. I think diagonalizable if and only if the minimal polynomial for T has the form that x minus c1, x minus c2, x minus ck, and that means that the minimal polynomial is actually completely factorized into distinct linear factors. So this is not, but it is, but the minimal polynomial, but here k being greater than 1, let me write in statement, k being greater than 1, not complete, not diagonalizable. Okay, so that means a non-zero nilpotent linear operator is not diagonalizable. That's one fact. Okay, so that means T cannot be diagonalizable as a statement, correct, but as a option for this question, this is false option. But as a option, this is not a option, because here it is asked to which are the incorrect option. We have to find those. So this is not the incorrect option. This is the correct option. Third fact is that if the index of t is r, so what is the index? That is the smallest positive integer for which t to the power r equals to 0 for a nilpotent linear operator, and dimension of v is n, then the degree of the minimal polynomial is r. That's correct, because for a nilpotent linear operator, the minimal polynomial, characteristic polynomial is x to the power n equals to 0. That's clear. Characteristic polynomial is x to the power characteristic polynomial f of x, that is x to the power n, and the minimal polynomial must be some mx, right? Some mx equals to x to the power k for some k less than equals to n. Okay, but as t is non-zero, so k must be greater than 1 as well. But the fact is that if index of the linear operator is t for the nilpotent linear operator, that means t to the power k is equals to 0. But if the index of the nilpotent linear operator is r, then t to the power r is equals to 0, but t to the power r minus 1 is not equals to 0. So that means the minimal polynomial is only exactly x to the power r. So here it is r, I am saying k. So let me change that to r as well. So that's why if this option is correct. If the index of t is r, dimension of is n, then the degree of the minimal polynomial is r. That's correct statement. So as a statement, this is correct. So this is not an option for our question. Fourth option, if index of t on v is r and dimension of v is n, such that r is greater than equals to 3, then t may be diagonalizable. Okay, so no, this is also not possible, because index of t is r, so that means x to the power r is equal to 0. This is the minimal polynomial. So now if r is 3, then minimal polynomial is actually not in this form, that x minus c1. I mean t will be diagonalizable if and only if the linear operator minimal polynomial for the linear operator must be of this form. This is what is the statement I want to mention in this. This is very important theorem actually. This is very important theorem. Okay. So minimal polynomial has to be in this form. That means it has to be distinct factor, and C1, C2, Ck will be distinct. Okay. So here is Ci are distinct eigenvalue. Okay. So that's why this statement is incorrect statement. Oh, sorry, here is the question. This statement is incorrect statement, and as an so as an option it is correct. So as a statement this is incorrect. So this is what it is for this problem. So if you have any problem or anything not clear to you in this specific problem, you can ask, or anything you are encountering during the this course material, you can also ask. So is there any problem? This problem is very interesting and very important problem, because that summarizes many conditions or many statements or many facts of the diagonalizability. So please look at carefully and rethink if there is any doubt in this problem. So you can ask me. Okay. Okay, I hope this is clear. Even this problem is not clear to you. Any very simple facts is also not clear to you. You can ask, and I'll try to explain those things. So basically, what are the very important facts you should you should remember? First is that minimal polynomial always divides the characteristic polynomial. First fact. Minimal polynomial is monic polynomial, and that is the smallest degree polynomial which annihilates the linear operator t. That means if you have a linear operator t, and if you have a polynomial which annihilates the linear operator t, that polynomial will be divisible by the minimal polynomial. Second fact is that T will be diagonalizable if and only if the minimal polynomial must be of this specific form, that x minus c1, x minus c2, x minus ck, where x1, c1, c2, ck are distinct eigenvalues for the linear operator T, and they are all of the distinct eigenvalues. There is no other. Okay. Third fact is that the minimal polynomial and the characteristic polynomial will have the same roots but different multiplicity. Okay. And that multiplicity, in characteristic polynomial, the multiplicity will be bigger, because we know that minimal polynomial divides the characteristic polynomial. So that's why the multiplicity, if x minus c d1, this is the multiplicity in characteristic polynomial, and x minus c1 whole to the power some m1 is the multiplicity in the minimal polynomial. So in that case, m1 must be less than equals to d1. Okay. So these are the important facts you should keep in mind. And another fact is that if t is a nilpotent linear operator, then the characteristic polynomial will be x to the power n equals to 0, where n is the dimension of the vector space V over which the linear operator t is defining. Another fact is that the minimal polynomial will be x to the power some k is equal to 0, and k is the index of the nilpotent linear operator t. These are the facts. Okay, even if you have any problem, you can ask. So I'm going to the next problem. During that, even if I'm solving this next problem, and during that, if you have anything doubt to the previous problem or anything to the course content, you can ask here, and anything to the previous tutorial also. Okay, so let's get back to the next problem. So what is the next problem? Says that let V be a vector space of continuous real valued functions on the interval -1 to 1. Okay. And let W and W naught be the subspace of even and odd functions. So what is even and odd functions? That I will mention. And and let T be a linear operator on V defined by this. Then which of the following statement is or are incorrect? Here it is, the question is correct. So we have to find the correct options. So a function if from here -1 to 1 to real number is said to be an even function if f of minus x is equals to f of x for all f of minus x equals to f of x for all x belongs to -1 to 1, that whatever the domain, and odd if f of minus x is equals to minus of f of x. So that means a function can be even, can be odd, and can be none of this. That means the function can be not an even function, not an odd function. For example, f of x is equals to x square plus x. So note that f of minus x is equals to x square minus x. It is not minus of f of x, and it is also not f of x. So that means a function need not be a even function or odd function. But interestingly, every function can be written as a sum of even function and odd function. So that means a function need not be an even function or odd function. Okay, that's first fact. A function can be something that is not an even function, even not an odd function. But every function f of x can be written like this way: f of x plus f of minus x by 2 minus f of plus f of x minus f of minus x by 2. So if we consider this is the capital F of x and this is considered as g of x, so then clearly look at the carefully, f of minus x is equals to f of x again, and g of minus x, that will be minus gx again. So that means this is an odd, this is an even function, this is an odd function. So every function can be written as the sum of an even function and an odd function. But a function need not be independently even function and odd function. So one fact here it is that if the vector space is something like that, it is sum of two terms, sum of two type of terms. That does not imply that they will individually, I mean, if a vector space V is equal to something like V1 plus V2, and V1 has some property and V2 has some property, that does not imply that V will have the property of V as well as V2. That is not guaranteed. Okay. So that means the set of all function here, that is continuous or not continuous, that's separate fact, that can be written as a sum of two vector space. One is the sum, one vector space is the space of all even function, and one vector space is the space of all odd functions. Okay, so whatever it is. So this is what it is. W is the space of all even function, and WO is the space of all odd function. This is what it is mentioned. Okay. So now let's go to the so T is here. It is linear operator from the space of all functions, continuous functions from minus one to one. So the question is WE is invariant under V. So what is mean by invariant subspace? Let T from V to V be a linear operator, then a subspace W of V is said to be invariant under T if T of W belongs to capital W for all W belongs to capital W. That is, in short, T of W is subset of W. That means T will map every element in W to the element of W. Okay, this is what it is mean by this is what it is mean by invariance. So invariance means that it will not it will map every element of that space to the again to the elements to that same space. Okay. So now the first option is that uh, first option is that whether WE is invariant under T or not. So parallelly one can ask whether WO, that is the odd function collection, that is again invariant under or not. So if you know how to solve one, then you'll know the how to solve the other. Okay. So first fact is that first option I'm right A. So WE is the sets all f continuous function from -1 to 1 to R continuous such that f of even function f of x f of minus x equals to f of x. So whether WE is invariant under or not, and T is the linear operator from V to V. V is the space of all continuous functions from 0, 1 to minus 1 to 1. Okay. So here V is equals to all those functions from minus 1 to 1 to are continuous. This is a collection of all continuous functions basically. Now T of f is a new function which at the point x is saying that 0 to x f of t dt. I hope this is the operator, yeah, 0 to x f t dt. So whether this linear operator sends an even function to even function or not, the answer is no. For example, let f of x is equals to x square. This is an even function. So f of x is actually v. Here it is. Sorry, not only v, this is in WE. So now T of f at the point x is equals to 0 to x t square dt. So that will give t cube by 3 0 to x, and that will give x cube by 3, and this is an odd function. So that says T of f is not in WE. So that means WE is not invariant under T. Under T. So that means that first option is, here it is asked to find the correct option. So first option is not correct. Yeah, first option is not, W is invariant under T, that's not correct. Second fact is that V is actually the union of WE and W naught. So what is W and W naught? W is the even function and WO is the odd functions. So V is actually, it is saying it is union of W naught, and that is also not correct. Why? V actually, here V is actually, here, so for second option, here V is actually WE plus WO. Okay, but that is not equal to WE union of WO. Okay, one second. That is not equal. So union means, for union of two sets means that is an element in either in WE or in W naught, or in both. First of all, WE, also note that here, note that WE, the space of all even function, intersection WE, W naught, that is the space of all odd function, that is equals to 0. There is no function which is except 0 function which is both even and odd, because even function mean f of x is equals to f of minus x is equals to f of x, and odd function means f of minus x is equals to minus of f of x. So that means from this you will get that f of x is equals to 0. So there is no other function. If a function is even and odd, then that function has to be 0. There is no other option, that function can be anything. Okay, so that means this is 0, but still that does not guarantee that V is actually the union of these two sets. Union means V there, I mean, if we take any element from A and B are two set, for example A and B are two set, if we take any element x belongs to A union B, that implies that either x belongs to A, or x belongs to B, or x belongs to both A and B. Okay, but for the last option, fx is equals to x square plus x, this is neither even nor odd. So that means this is not in WE, this is not in WE, not in W naught. Okay, so that means that can't be in W. That implies that f of x is actually not in the union of WE union W naught. Okay, but fx is in the V, right? Fx is continuous function from minus 1 to 1, but fx is in V. So that implies that V is actually not equals to W union W naught. And now, so that means that option is incorrect. But one fact I just want to remind you, if you remember in maybe in the first or second tutorial, I have tried to explain that two subspace of a vector space, their union will be again a vector space if one is contained in other. But here WE, neither W is contained in W naught, and W naught is neither contained in WE. Union of two vectors, I mean, if you have a mother vector space V and you are considering two subspace W and V1 and V2, then V1 union V2 will be again a subspace of the vector space V or a vector space itself if and only if that one of the vector space is contained in other. So here it is not possible. Neither the even function space is contained in the odd function space, or nor the odd function space is contained in the even function space. Okay, so that's why the second option is also incorrect. So this is also not our option. Now the question is neither W nor W naught is invariant under T. This is correct because W is not invariant. W is invariant under T. That's false. That means W is not invariant, right? And similarly, that what I have proved using the x square equals x square, we have proved that WE, that is the space of all even function, continuous function, that is not invariant. Now, if you choose f of x is equals to x cube, then this is an odd function, right? So this odd function is also, if you take integration, you will get the x to the power 4 by 4, right? But x to the power 4 by 4 is an even function. So therefore, the linear operator T basically maps odd function to even function to odd functions. So therefore, the even space of all even function is also not invariant under T, and space of all odd function is also not invariant under T. So as a option, this is correct. Here it is asked, neither WE nor W naught is invariant under T. And fourth option is also incorrect. The W naught is invariant under T. I hope so. This is clear. If there is any doubt, please let me know. I will try to explain. Anything very simple is also okay. If you have any doubt, please uh, let me know. Yeah. Hmm. Yes. Yes. No, 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 no. It's not. It's not true. It's not true. Let me. Every even function will be odd function. No, uh, it's uh, that's interesting question. Suppose you have cos x. This is an even function. Cos of minus x is equals to cos x. This is an even function. So if you take integration, that will be sin x minus sin x and 0 to x. So sin t 0 to 2, that means minus sin t, and sin 0 is 0. So that means sin t as an f. This is sin t. So uh, this is an odd function because sin t is odd function. So minus sin t will be odd function. But every even function after integration will be odd function. I hope it's true for the continuous functions at least. I hope it's true. Every even function after integration will be odd function because here you have continuous functions on a compact interval. So you can yeah, it's true. It's true. It's definitely true in this context, but I don't. Just if we start with the space of all continuous functions on a compact set minus 1 to 1 like this, then this statement is correct. Every integration of every even function, integration in this way like 0 to x, 0 to x this way. But one fact, let me write sin t. If you take and you are considering 0 to x dt is equals to integration is minus cos t. Okay, sorry. Cos x integration is minus sin x. No, cos x integration is just sin x, not minus. Okay. So sin t integration is minus cos t and 0 to x. So what it will be minus cos x minus minus plus cos 0 is 1. So now if you take this is the t of f at the point x, then this is suppose g. So g of minus x is equals to minus cos of minus x plus 1. This is equals to minus cos x plus 1. Yeah, this is true. This is true. I'm not able to. I'm not saying just only on the these observations, but this will be true because there is a theorem you can develop. I mean, whatever right now it feels to me that suppose you have a continuous function f of x, right? And and I think if it is even function, then you can take it as a limit of a set of even function f of nx, and you can use the dominating convergence theorems, and from there you can say. But I believe there will be some very easiest argument for this without not using that much fancy stuffs like dominated convergence theorems or anything. But this may be true. This is true. Okay, so is the question is either like this one or any other about this? Uh, so that means it's true. I mean, basically what I have to say that if you have a even function f of x, you can get a sequence of even functions f n x that converges to f uniformly on complex subset -1 to 1, and uh, then f of integration f of t 0 to t 0 to x f of t dt, that will be actually equals to limit of n tends to infinity 0 to x f of n x n t dt. Now, as each of them are f and t being even function polynomial, this is a sequence of polynomials. This is what is the interesting fact. If you have a even function, you can get a sequence of polynomials. I mean, okay, let me state it clearly. Okay, whatever is the correct thing, let me state. This is option is correct, but whatever the argument I am giving, that argument may be not clear to you everyone if you are not knowing the major theory and anything. Thing is that let f be a even function. Then there exists a sequence Pnx of even polynomials such that Pnx converges to f of x uniformly on 0 1. This is not 0 1, that whatever the complex set -1, 1. This can be any compact interval. And this is called the Stone-Weierstrass theorem. Weierstrass theorem, not Stone-Weierstrass theorem. This is Weierstrass theorem. Next thing is that, and this fact will say that integration 0 to x f of t dt, that is equals to limit n tends to infinity integration 0 to x pnt dt. Okay, so pnt is actually the polynomials. Okay, so now pnt are even polynomials, so their integration will be odd again, and the limit of odd will be odd again. So in that way you can say. So I don't know that whether you guys know this. This is dominated convergence theorem. Here it is using the dominated convergence theorem, and here it is using the Weierstrass approximation theorem. Okay, so if you have any other doubt on this regarding, you can just tell me, and any other person, if you have any doubt, you can just tell me. So if you don't have any problem, so I'm going to the next problem. So what it says, let t from be a linear operator on the vector space of all polynomials and polynomial functions of degree less than equals to 3. Define the linear operator t is like this way. Then the characteristic polynomial of t is, okay, so I have to find, as I have said, if you want to find the characteristic polynomial, what it is the characteristic polynomial f of x, that is basically determinant of xi minus the matrix representation of t with respect to any order basis. Okay, because similar matrices have the same characteristic polynomial, so that's why this is what it is. So now let's first find the let b is equals to 1 x square x cube is the order basis of v. Okay, the linear operator t. This is the vector space v, let. Okay, then what it is mapping, t mapping 1 to where it is mapping, t mapping 1 to x cube. Okay, t x mapping to x square, and t x square is mapping to x, and t x cube mapping to 1. So the matrix representation of t with respect to the operator b is actually 0 0 0 1 0 0 1 0 0 1 0 0 1 1 0 0. This is the matrix of t. So now we have to find the determinant of this. So determinant of x minus tb, x identity minus tb, that is equals to x 0 0 minus 1 0 x minus 1 0 0 0 x, there will be minus 1 here, yeah, 0 0 0 0 x, I think here is the minus 1. So now I think this determinant has very simplest way to find, so but let me go to with the whatever the standard way. X minus 1 0 minus 1 x 0 minus 1 sorry 0 0 0 x, then this is the determinant and this is plus minus plus plus minus plus minus, this is minus 1, so this will be plus 0 x minus 1 0 minus 1 x minus 1 0 0. So let me find these two, this determinant x of x cube, first one, and the next one is the minus 1 minus minus plus, that is minus x, plus it will be like 0 and it will be minus x, so minus x minus minus plus x again, yeah, minus x, sorry, minus minus plus 0 minus minus x, yeah. Next is the plus, that is minus 1 into my 0 minus 1. I hope I am writing correctly. X cube minus x square plus 1. So this will be x to the power 4 minus x square plus 1. That will be x to the power 4 minus 2x square plus 1. So let me. This is the question number 3. Yeah, this is correct. So this is correct. So this is what is the characteristic polynomial. So that means this can be written as x square minus 1 whole square clearly, and that can be written as x minus 1 square x plus 1 square. This is the characteristic polynomial. Okay, this is the characteristic polynomial. So now what is the question here? It is asked that characteristic polynomial of t is x to the power 4 minus 2x square plus 1. This is correct option. Second option, the minimal polynomial of t is x square minus 1. So minimal polynomial will be, this is if t square is actually, so that means the minimal polynomial will be x square minus 1 if t square minus identity is equals to 0, that is t square is equals to identity, right? So let me check whether this is correct or not. So what we know that t of 1 is actually x cube, t of x is actually x square, t of x square is equals to x, and t of x cube is equals to 1. So now t square of 1 is equals to t of x cube, and this is equals to 1. T square of x, which is equals to t of x square, which is equals to x. T cube of x is equals to, sorry, t square of x square, that is equals to t of x is equals to x square, and t of x cube, t square of x cube, which is equals to t of 1, which is equals to x cube. So that says that t square is equals to identity, and clearly t is not equals to identity. Clearly t is not equals to identity. That says the minimal polynomial is x square minus 1. This is correct. Because, okay, another way. So, okay, whenever you have the characteristic polynomial is x square minus x minus, the characteristic, if you remember the, if you look at carefully, the characteristic polynomial is x minus 1 square, x plus 1 square. So here is one fact I am saying out of the this problem, that whenever you have a characteristic polynomial look like this way, then what are the possible of minimality polynomial? One fact is that the minimal polynomial and the characteristic polynomial should have the same roots. So therefore, the minimal polynomial should be at least plus 1 and minus 1 factors will be there. Minimal polynomial, at least this will be. This is one option. Another option is that x minus 1 square x plus 1. Another option is that x minus 1 into x plus 1 square. Another option is that x, what is the characteristic polynomial, that itself is the minimal polynomial. So these are the 4 options of minimal polynomial. Whenever you have a characteristic polynomial look like this way, the minimal polynomial options are these. Okay, note that out of these four options, only this option is the possibilities of options where the linear operator will be diagonalizable. Okay, because in that case only the minimal polynomial is completely factorized into distinct linear factors. And apart from this, there are the three more options, three more possibilities options, which is the minimal polynomial. But in our case, it is itself this is right, that x square minus 1, that means x minus 1, x plus 1, right? So these are also possible options of the minimal polynomial. This fact, I hope this fact is clear, because this is very interesting fact, and these are very interesting way to look at the minimal polynomial from out of a characteristic polynomial. Okay. So whenever, so basically what I want to say, whenever the characteristic polynomial is look like this way, then the possible minimal polynomials will be these four options. Only these four options are the possible. Okay. But only one option of them is actually the case where t will be diagonalizable. But in our case, this is the option, and that we have already separately checked. So that means what I just want to say, if the characteristic polynomial is this, then minimal polynomial can't be this or this or x minus 1 or x plus 1. These are the not possible choice. These are the not possible choice. That individually, if you consider individual one factor, these are the not possible options for the minimal polynomial, because minimal polynomial and the characteristic polynomial should have the same root. Okay, because here the whatever the option I have written in just last that x minus 1, x plus 1, x minus 1 square or x plus 1 square, all of the options will divide the characteristic polynomial, but that does not guarantee that they will be minimal polynomial. If it wants to be a minimal polynomial, it should have at least the same root as the characteristic polynomial. Okay, so as I have said, diagonalizable, that's also correct. Minimal polynomial is x square minus 1, that's correct. Then t is not diagonalizable. This is false, because t is diagonalizable. If the characteristic polynomial is minimal polynomial is this, then the characteristic minimal polynomial should be in this form. That is completely factorized, so that's why it is diagonalizable. Geometric multiplicity of 1 is 1. That's not correct. So this is one fact I am using. So what is the geometric multiplicity? What is the algebraic multiplicity? So algebraic multiplicity I have already mentioned once, but still I will mention algebraic multiplicity and geometric multiplicity. If C be a eigenvalue or characteristic value for a linear operator T on a finite dimensional vector space, T on a finite dimensional vector space V, then the largest number are then the largest number di or d such that x minus c whole d divides the characteristic polynomial. So that means if c is an eigenvalue, if c is not eigenvalue, then d will be 0. That means there is no factor like x minus c. Okay, and you know eigenvalues are nothing but the roots of the characteristic polynomial. Okay, so the largest power in that characteristic polynomial, that is the algebraic multiplicity. This is what it is, the algebraic multiplicity. And the geometric multiplicity the dimension of the space T minus Ci whole x is equals to 0. Basically x belongs to R, x belongs to the vector space V such that T minus Ci whole x is equals to 0. That is the dimension of the eigenspace. This is called eigenspace. Eigenspace corresponding to the eigenvalue C. So if C is not an eigenvalue, then there will not be any non-zero vector, so dimension will be 0. If C is an eigenvalue, that means there exists a vector x such that Tx is equal to Cx. That means the dimension of this space will be at least 1, and C being an eigenvalue, x minus C will be a factor in the characteristic polynomial. Okay, so basically dimension of the space, this space is the geometric multiplicity, and geometric multiplicity is always less than equals to algebraic multiplicity. This is interesting fact. This is a theorem itself, but I will not prove this, but you just mention this. And if diagonalizable, T will be diagonalizable. This is one theorem. T will be diagonalizable if and only if geometric multiplicity is equals to algebraic multiplicity for all the eigenvalues, or characteristic values. Because note that why that is, I just want to say that suppose you have a linear operator T and you have its characteristic polynomial f of x is equals to x minus c1 whole to the power d1 all the way x minus ck whole to the power dk, and here is the c1, c2, ck are the distinct eigenvalues. Then f is a polynomial of degree n, so therefore that should give that d1 plus d2 plus all the way plus dk is equals to n, right? And another fact is that geometric multiplicity is actually what I am saying. Let geometric multiplicity is m1, that is corresponding to c1, m2 all the way mk are geometric multiplicity. That is the number of that is the dimension of the eigenspace corresponding to Ci. So that means the corresponding to the eigenvalue Ci, there is the mi number of distinct eigenvalues, mi number of linearly independent eigenvalues, okay, eigenvectors, sorry, mi number of corresponding to the eigenvalue Ci, there is mi number of linearly independent eigenvectors. Now, one fact is that mi is less than equals to di, that is what it is I'm saying. So, but if T is diagonalizable, then the set of all eigenvectors corresponding to the distinct eigenvalues, I mean linearly independent eigenvectors, they will form a basis. So that means m1 plus m2 plus all the way mk, this has to be equal to dimension of n, dimension of the vector space V, which is equals to n, and this must be equals to each of them are equals to less than equals to d1 d2 summation of d1 plus d2 plus all the way plus dn, and that is equals to n. So there is no other option that di is equals to mi, except this option. There is no other option for which this should hold, right? There is no other option except this, that this should hold. So that's why the geometric multiplicity will be equals to the characteristic multiplicity for the in the case of diagonalizable, and this is if and only if condition. But this fact is also easy, that geometric multiplicity is actually less than equals to algebraic multiplicity. But I just don't want to mention here because that will take a little time more. So whatever it is, but that will say that geometric multiplicity of 1 is 1. That's false. Because why this is false? Because in this case, whenever the characteristic polynomial is this one, that x to the power 4 minus 2x square plus 1, which already mentioned, in that case the characteristic polynomial is something like x minus 1 square x plus 1 square. So what it is says, the geometric multiplicity in this case, algebraic multiplicity corresponding to the eigenvalue 1 is 2. That is not equal to the geometric multiplicity if the geometric multiplicity is 1. But we know that T is diagonalizable. Okay, so let me say here algebraic multiplicity of 1 is 2. Okay, also T is diagonalizable. That should imply geometric multiplicity should be 2. So that can't be 1. So that's why the last option is incorrect. So is it clear? If you have any doubt, anything you want to explain, I should explain, you can ask me. I'll try to mention. So this fact is also not very easy. They are not very tough. That the geometric multiplicity is less than equals to algebraic multiplicity, because suppose geometric multiplicity. I just quickly try to mention. Suppose you have geometric multiplicity m1. So that means you have m1 number of eigenvectors. So that means if you just want to form a basis, suppose m1 number of eigenvectors, that is like v1 all the way vm1. This is the basis. This is the basis linearly independent vectors in the corresponding eigenspace of C1. So now you can extend it to form a basis, right? But these are eigenvalue. So the matrix of this of the linear operator T corresponding to this eigenvalue, this basis will be something like, first will be like corresponding to this eigenvalue, this being eigenvector, this will be like C1, M1 times C1 will be there, and whatever will be term it is below. So if you take the determinant of x minus this one, so you will have x minus c1 this factor m1 times, right? So that means the algebraic multiplicity, which is actually x minus ci to the power whatever the largest largest appearance of x minus ci, that is the algebraic multiplicity. So if you have geometric multiplicity is m1, then the algebraic multiplicity should at least contains m1 number of factors repeatedly. Okay, so this is what it is. Even if you understand, it's good. And if you want to understand this explained explicitly, then ask me. I'll try to explain. But this is not explicitly not needed for this. But for your conceptual part, you need this explicitly. Okay, so let me go to the next problem. So what it says, let T be a linear operator on R to the power 4. Let the matrix representation of T with respect to the standard basis of R3 is 1, 2, 3, 3, 2, 1, 0, 0, 1. Then T square minus T cube minus this is okay. So clearly this is a polynomial of degree 3. Okay. So if a polynomial of degree 3 has to be vanish, so what is the well-known polynomial which has to be vanish of degree 3? That is a characteristic polynomial, because Cayley-Hamilton theorem says that. Okay, so let me write the Cayley-Hamilton theorem. Every linear operator T or matrix, linear operator T on a finite dimensional vector space V must, what is called, will be annihilated by the characteristic polynomial. It will annihilated by the characteristic polynomial. Okay. So what is the degree 3 polynomial? Characteristic polynomial is degree 3, and that is monic polynomial. So one can directly try to find what is the characteristic polynomial for this for this matrix. So here a linear operator T with respect to the standard order basis. Standard order basis means 1, 0, 0, 0, 1, 0, 0, 0, 1. So you can directly write the matrix of this is actually 1, 2, 3, 3, 2, 1, 0, 0, 1. So x minus t, determinant of this is actually x minus 1 minus 2 minus 3 minus 3 x minus 2 minus 1 0 0 x minus 1. So you can expand it from the above, but I will expand it from the below, from this one. So x minus 1 x minus 1 x minus 2 minus 3 into 2, because this is correct, I hope. X minus 1 into x minus 1 x minus 2 minus 3 2, this is correct. X minus 1, this will be like x square minus 3x plus 2 minus 6, that is equals to x minus 1 x square minus 3x minus 4. So this will be x minus 1, this will be like x squared minus 1 x 4 minus 1. Oh God. X minus 4x plus 1. So let me write x square minus 4x plus 4 x square x square plus x minus 4x minus 4. So this is correct. So this is the characteristic polynomial, okay? This is what it is called fx, which I am standardly trying to denote. This is fx. So then all the eigenvalues are distinct. So many questions can be answered from the facts whatever I have tried to mention earlier. All the so what are the eigenvalues? Eigenvalues are 1, 4, minus 1. This is first fact. So only possible option for, I'm not going to the options. So what are the, just looking at the characteristic polynomial, what we can say as much as possible. Eigenvalues are 1, 4, minus 1. Only possible option, only possible choice of minimal polynomial is itself. X minus 1, x minus 4, x plus 1. Why it is? Because here all the eigenvalues are distinct. So minimal polynomial should contain all the factor at least once, and here is all the distinct factors. So that will be, and minimal polynomial should not exceed, the degree of the minimal polynomial should not exceed to the characteristic polynomial. So but here it is asked to me that t cube minus 4t square plus t plus 4i. So let me go to the, in this direction. So if you expand it, what it will be, x cube minus x cube, yeah, t4 was there, oh, no, t cube, okay, x cube minus 3x square minus 4x minus x square plus 3x plus 4. So what it will be, this will be equals to, I'm just directly trying to write x cube minus 4x square minus x plus 4, x cube minus 4x square minus x plus 4. Is it the first option? Minus plus, okay, there is a plus, it is x cube minus 4x square plus x cube, okay, x cube minus 3x square minus 4x minus x square plus 3x. So this is the incorrect option. So that means this is a not correct option, because here it is, we are getting minus t, but here it is getting plus t, and there is no other polynomial of degree 3 which should annihilate. And monic polynomial, there will be no other polynomial. And in fact, if a polynomial should annihilate a linear operator, and in this case the minimal polynomial is also same, right? This is what it is. So let me quickly check once, x square minus x minus 4. So what it is, x cube minus 4x square minus x plus 4. Yeah, there will be minus. So this is not correct option. So this is what it is, and so that says t is diagonalizable. That t is, because the characteristic polynomial is completely factorized into distinct linear factors, diagonalizable. And also you can look at from very easily that if you have distinct eigenvalues, so corresponding to each eigenvalue, there will be an eigenvector, and here is three distinct eigenvalues. So as you have three distinct eigenvalues, you have three distinct eigenvectors, and eigenvectors corresponding to distinct eigenvalue are linearly independent. So therefore, you have the three eigenvectors and which are linearly independent to each other. So therefore, that will form a basis, because you get a set of eigenvectors which are linearly independent, and that forms the basis, because there is no other option. If you have a three linearly independent vectors in a vector space of dimension 3, that will has to be a basis. So this is first option is not correct. Second option is that eigenvalues of t are 4, 1, 1. That is also not correct. This is also not correct, because eigenvalues are 4, 1, minus 1. Okay, that's why it is also not correct. Third option is that t is diagonalizable. That's true. And fourth option is that minus t to cube 8t square. Okay, let me simplify it. 8t square minus t to cube plus 2t plus 8i minus 8i, sorry, minus 8i. This is what it is, a 0. This is what it is claiming. Now if you take 2 common out, so that will get 4t t square minus t cube plus t minus 4 is equals to 0. Again it is false. So this is only one option is correct. I think there is mistake. Option B is only correct. T is diagonalizable, that's true. By Cayley-Hamilton theorem, a cube minus so t 2t cube. Sorry, I mismatched. So I have to do little different. Okay. So thing is that let's take these terms in the right hand side. This term to the right hand side. So what will get 2t cube minus 8t square minus 2t plus 8i. This is equal to 0. Let's take 2 common, t cube minus 4t square minus t plus 4 identity, that is equal to 0. And this is Cayley-Hamilton. This is characteristic polynomial, right? Polynomial linear operator of t, and this is 0. This is 0. So as this is 0, so this is equal to 0. So as this is 0, 2 times this will be 0, right? So that's why the fourth option is also correct. So is it clear? Okay. So if you have doubt, you can ask. These are very simple. Even if you have doubt, you can ask. Even it is being very simple, that does not affect. Okay. So let me go to the next problem, and even if you have till now anything doubt to the previous problem, you can ask. I'll try to explain those things again. So this problem. This is very okay. This is very important problem, and this is very, little difficult. Little. So let me read the problem. Let V be a vector space of n cross n matrices over the field F, and A be a fixed n cross n matrix over the field F, and T and U are B2 linear operator on V defined by TB is equals to AB. Okay. So A is the matrix representation of T. So what it is says, V be the vector space of all n cross n matrices. Okay, over the field over F, and A be a fixed n cross n matrix, T and U, but linear operators on V. So T is actually giving from V to V. T is giving any matrix B sending to AB, any matrix B, and U is from V to V. That is V. U of B is equals to AB minus BA. Okay. Then which of the following statement is incorrect? If A is diagonalizable, then T must be diagonalizable. Minimal polynomial of T and A are same. If A is diagonalizable, then U must be diagonalizable, and minimal polynomial of U and A are same. Minimal polynomial of U and A are same. Minimal polynomial of T and A are same. If A is diagonalizable, then U must be diagonalizable. Okay. So here is one fact. It will be better if we can quote that. So V is actually the vector space of all n by n matrices. That is actually the denoting by M over the field F. Okay. Okay, here is a little risk, whatever the method I will take, because that will take little time if it is not correct. Okay, so if n by n, right? N by n. So note that Eij, which is equals to the matrix. First, let Eij equals to let Eij is equals to the matrix, the n by n matrix with only non-zero entry. So this is n by n written also, right? So I have to take little different method, I think. Okay, let me write n by n matrix with only non-zero entries. Entry 1 at I comma z place. So then Eij such that I runs from 1 to n, and then j runs from 1 to n. So for I equals to 1, so here is the ordering I'm mentioning like this way. For I equals to 1, so let me just quickly check this one. 1 0 0 0 and 0 0 0 0 1 0. This is 1 0 0 0 1. So if you have B, so this is the basis, and you have a matrix A is equals to Aij. So now this is the left multiplication. Left multiplication by Aij. So suppose A equals to Aij. This is something I'm just quickly checking, and from this quick checking also you can answer. There is no problem. So B is sending. So that means this it will send 1 0 0 1 to the matrix. This will be like A11, A12, A21, A22. So this will be A11. This will be 0. This will be A21. This will be 0. Okay. So this method is maybe not going to work then. Okay, so I have to hit one by one. I have to hit one by one option. I just wanted to hit it by single stroke, but right now I'm not able to find. I mean, there is. I believe this is the way, but we have to consider some different order basis. So for which this can be done by single hit. But okay. So what it is giving? A is a fixed matrix, and that is giving by like this way. So first option is that option A is asked. What is the option A? That A, if A is diagonalizable, then T must be diagonalizable. This is the option. If A is diagonalizable, then T must be diagonalizable. So if A is diagonalizable, then there exists an basis. I mean, I don't want to write the basis. Then there exists an invertible linear operator T, linear invertible matrix M P, such that T with respect to the order basis Eij, okay, beta is equals to, sorry, T not A with respect to, or A, there is no order basis, so A will be equals to, P inverse D, and diagonal operator D, such that, so this will be right. If A is diagonalizable, then A will be equals to P inverse dP for some invertible. Sorry, D is equals to P inverse D is equals to P inverse AP. That means there is an invertible matrix P which will diagonalize the linear operator T. Okay, now uh, this is what it is. What we have. Yeah, D. Sorry, diagonal matrix. There is a diagonal matrix D. That's true. Thank you. Matrix D is such that D is equals to P inverse AP. Okay, so this is what it is. Diagonalizability meaning for a matrix. So the question is that T is diagonalizable or not. So if you can find a basis B, basis for the beta, such that this happens, so then we will be able to. Let's take beta is equals to Eij, such that Eij are the matrix. Eij is the n by n matrix. So let's take D is the diagonalizable, that D is the diagonal matrix, that is D11, all the way dnn. This is the diagonal. This is the generally written like this way. D is equals to diagonal this. That means the diagonal entries are d11, d22, d33, dnn, and all other entries are 0. Here is the n-cross-n matrix with only non-zero entry is 1 at I comma j place. Okay, this is what I am taking a basis. You can give an ordering anyway. But if I can prove that t of eij is equals to something, so that will be better. So t of eij is equals to, so t of eij is equals to a into eij, right? And a into eij means, um, for example, I just want to know one. This is one very simple thing I want to know. Suppose you have aij matrix and it is 1 and all other entries are 0, 0, 0, 0, 0, 0. So what I will get? This one will be 0, this one will be a, this one will be like a1 1 will be 0, a1 2, and this will be 0, this will be a2 2 0, a3 2. And if I take 1 is in this place, so what I'll get? I'll get first of all this entry 0, second entry 0, third entry is a 2 1. Ah, this is interchanging ij row basically. Yeah, not interchanging ij row. Okay, let me write this one first of all. This is equals to p a is equals to p d p eij. Okay, now d is diagonalizable, so there will be some p inverse. Okay, p inverse eij. So d is diagonalizable. So that means hmm? No, if I write mm, a1 2 it will be a1 2 it will be, but that's true. A1 2 it will be, and this one second option. So basically, second option will be like 2 1 2 2 2 3. So this will be like 2 2. I think a 2 2. Next option will be like a 3 2. This is not helpful. Interchanging second row to the first row. This is not helpful. So let me write in the other way. So I just don't want to use the heavy terminologies. So if I use heavy terminologies, then it will be very easy. So this is what it is. So T look like this way. There is no problem with this. So what I want to show that P is actually similar to a diagonal matrix, right? Hmm. T is similar to a diagonal matrix. This is what I have to show. Okay. Okay, I have to find the correct option. So correct option or incorrect? Incorrect options. You have to which of the following statement is incorrect. So to find the incorrect option, right? So these are the very interesting statement. If A is diagonalizable, then T must be diagonalizable. Okay, so let me go to the heavy terminology then. I don't want to use it. So let um, T T maps T maps B to P P D P inverse B. Right. If I can think like that, I have to prove that T is equals to T of B is equals to. Okay, so let um, let P from MNC, MNF, MN here it is F, right? Vector field is the field F. Let MNF to MNF be a linear transformation, which is given by phi sending any matrix B to P inverse B. P is that matrix. This is the P. P inverse B. Then phi should map TB, which is actually P inverse of AB, right? And this can be written P inverse AP and PB, right? So then this can be written as diagonal operator D, and PB is actually PB, right? So what it is saying is that uh, phi is this says that as P is invertible. Yes, yeah, thank you. So this is means this is isomorphism because this is invertible. Okay, that's why it is isomorphism. This is isomorphism. So phi from TB to this will map B equals to PB. So phi is an isomorphism. So that means the matrix representation of uh, if you have isomorphism from one side to other, there will be an invertible matrix. Suppose you have an isomorphism A, not A, I can't use A, phi from a vector space V to V. That means there is just an invertible matrix whenever it is isomorphism such that X is equals to uh, P X is equals to that invertible matrix um, invertible matrix like here it is some Q into X, right? This is what it is. Now, so then PTB also, yeah, PTB, whatever it is, that will be equals to P inverse of TB. This is what it is by formula, right? So that implies that D of PB is equals to P inverse of TB, and PB is equals to P inverse of B. So, okay, one second. So this basically what I'm getting here actually. D of P inverse B is equals to P inverse of TB. This is what I'm getting. So now TB is equals to, this is what I'm just repeating the things. That's not what it is. So no. This is not what I'm recording. So P of TB is equals to P inverse of TB. That's true. There is no doubt about this. And P of TB is equals to D PB. now so P is actually, here it is similar to the, so now if I take Eij as the basis, then TB, acha, okay. So from here what I can say is that TB is equals to, okay, let me do it for the 2 by 2 matrix, so it will be better, not going to the very, so if I just do only the 2 by 2 matrix, so what are the bases? Bases are like E11 that is equals to 1 0 0 0, and E12 that is equals to 0 1 0 0, and E13 that is equals to 0 1 0 0, and E31 that is equals to 0 0 0 1. So now if I write A is a matrix, A is diagonalizable, that is A11 A12 A21 A22, this is the matrix A, and let's take D is the diagonal matrix where it is diagonalizable, D11 0 0 D22, this is the diagonal matrix, that is A, there exists in matrix P such that P in or P equals to D. Now the question is that now T is mapping EI11, where T will map E11 is equals to AB. So that means this will be like A11, A12, A21, A22. This will go to, yeah, now I got it. 1001, where it will go the first row, first column, I think. This will be 120, the first column, and 00. And T of E21, E12, that will go to the A11, A12, A21, A22, and this will be like A12, 01, 00. This will be like a 0. This will be like A12, not A12, A2, A11, right? A11. This will be like 0, and this will be like A21. I hope I'm correct. Yeah, I'm correct. So T of E21, that will be equals to A11, A12, A21, A22, and this will be like 01, 00. So this will be like A12 and 0. This will be like 0, A22, 0. Yeah, and T of E22, that will again be equals to A120, A220. You can check, I think that's not it. So this is what it is. Now if you consider it is an order basis, now order basis I need to mention that carefully, so such that I'll get A11, A21, next one is A11, A21, A12. Yeah, so the order basis is that, let's consider the order basis is like this way: A11, E21, E12, E22. This is the order basis, as order basis. Consider this as order basis. Consider this as order basis. Then matrix representation of T with respect to this order basis beta is equals to, look at carefully, this will be like A11, A11, A21, 00, and next one will be like A12, A22, 00. Next one will be like Um, with respect to A1, 2 and T2, 2, 1, 2, 2, 2, yeah. So 0, 0, A1, 2, A2, 2, sorry, A2, 1, sorry, this is 2, 1, and 0, 0, A, oh, this is also 1, 1, I hope, yeah. This will be like A1, 2. You can check carefully. This will be the correct option. So this is what it is. So matrix representation of T with respect to this. So from here you can easily say, so this is basically A by A, right? Not A by A, 0, 0, A. This is the block matrix. So from here you can easily say if A is diagonalizable, if A is diagonalizable, then T is diagonalizable. There is no doubt about this. Diagonalizable. So that means the first option is correct option. What is the first option? A is diagonal, then T is diagonal. This is correct option. Minimal polynomial of T and A are same. That is also true. From here, why minimal? That is also the minimal polynomial of A is same with minimal polynomial of A T. Why it is? Because if minimal polynomial of A is P, then P of A should be 0. But as the matrix representation of 2 with respect to this block form is look like this way, then P of T with respect to B, that will be equals to P of A 0, 0, P of A. So now if P is the minimal polynomial, then PA must be 0. That means this is equals to 0, 0, 0, 0 as a matrix. This is not 2 by 2 matrix. This is a 4 by 4 matrix, and each of them are 2 by 2 block basically. So in generally you have to order in such a way that you will get matrix like this way n times. If you are considering it is on the n by n cases, then this will be a matrix of n times. So this is the ordering I first tried to consider, that E11, E21, E12. That means you have to consider the ordering for j fixed. You have to run I. For fixed j, you have to run I and it in that way. So the second option is also correct. Minimal polynomial of the, we have to find the incorrect option. So as an option, this is as a statement correct. So option is as an option it is wrong. Second option as a statement correct, but as an option it is wrong. Third option is that if A is diagonalizable, then U must be diagonalizable. So this is you have to check, if A is diagonalizable, then U must be diagonalizable. And the way you get AB, now we have to find the BA. Now for BA, what we can shortly answer. So now, for example, if you are using like this way, just one, I'll check that U of 1000, that is equals to A11, A12, A21, A22. This is with 1000 minus 1000, and this is A11, A12, A21, A22, and we know that first one is that A11, A21, 00, and second option will be like A11. Okay, third option is A12, fourth option is 00. So basically what we'll get, that 0 minus A12, A21, 0. Okay. Hmm. So what to do with this? This is the third option. Okay. So fourth option was what it is? Minimal polynomial of U and A are same. If A is diagonalizable, then U must be diagonalizable. If A is diagonalizable, then U must be diagonalizable. So here I have to consider some different order basis. But even that different order basis, okay, I think we have to take some other way so that it can be easily done. This should not take this much long time. Okay, okay. Another way is that. So let me forget about this. Suppose Suppose A is the diagonal matrix, that is PDP inverse, that is what it is we have. Now U of Eij, that is equals to, uh, right now I'm taking that A is actually the diagonal matrix. Okay, so that means this will be like Di minus Dj, Dii minus Djj whole into Eij. I think this is what it is. So this is, let's check this one first of all, then it will be clear. Yeah. So if, yeah, this is what it is. I'll just give you the check. This is will be correct. Yeah. So let A is equals to P inverse dp, uh, P inverse P inverse. So this is the diagonal, and her D is equals to diagonal of D11 all the way dnn, and then U of Eij, that will be equals to uh, P of dp inverse Eij minus P minus Eij P dp inverse, and you should check that this is what I'm just trying to write, that P of dii minus djj, this is the diagonal matrix right now, whose mm, this is scalar times Eij. This will be down, huh? This is what it is. Eij. Just check this one whether this is correct or not. And Dij. So that implies that if A is diagonalizable, that implies U is also diagonalizable. U is also diagonalizable. But interesting fact is that here the minimal polynomial is not correct. Why minimal polynomial is not correct? A is diagonalizable, then U must be diagonalizable as a statement correct. So as the option is false. Minimal polynomial of U are same, that is false as a statement correct. Why the minimal polynomial of U and A are not same? Because here the eigenvalues are changing. Clearly eigenvalues of U and A are not necessarily same. Therefore, they need not be have they need not have same minimal polynomial necessarily. So is it clear? I have taken the last question very long time, but I hope it's clear. And if it is not, please let me know. I'll try to quickly recall anything if I can do it quickly. Just check this one, this fact, Dij minus Djj Eij. This will be correct. We have to just check properly, and this will be correct because P is invertible, so that's it will be correct. Okay, so if there is any no doubt, so I will stop here. So next tutorial will be on the next Saturday. That is also till now, from this, at least in the next Saturday it will be 6 p.m. to 8 p.m. and I'll try to contact to the NPTEL team to change the date. Okay, thank you.